Hello everyone, I'm Rodrigo Benenson, and this is a video tutorial about weakly supervised semantic segmentation. This video is part of our ECCV 2020 tutorial on weakly supervised techniques for computer vision. So let's start by reviewing different image tasks. First, you have classification that asks, is there a cat at all on this image? Then you have detection, which asks where on the image is there a cat. Then you have semantic labeling that tries to annotate every single pixel that belongs to the cat class in the image. And then you have instance segmentation, which want to identify the different instances of cats and which pixels belong to each instance. So in this talk, we're going to mostly focus on semantic labeling because this is a task where most work has been done in the context of weakly supervised learning. The main goal of this talk is to give you the big picture in the field. We're going to discuss idea of more than 40 different papers, and I want you to have a framework on which you can understand different works, and then we're going to provide some specific examples, going a bit more depth in some of those papers. So since this is a video recording, please do follow through the video and do write down your questions. There will be a question answering session at ECCV that you can see on the ECCV website. And if you're watching this video on a video hosting platform, feel free to write down questions in the comment section and we will do a fair effort on trying to answering them. So let's start by revisiting the definitions. So fully supervised training means that you're directly supervising what do you want. So you're providing for each input image the desired output that you want to see out of your model. While when you're doing weakly supervised training, you provide indirect supervision, where the annotations that are provided do not tell the full story of the desired output that you want to have. An example here would be to have just partial annotation of a few points on the image. So in this example, let's see what are some of the challenges that you will have. So first off, a same class, in this case cat, can have very diverse appearance. So the little point that you have annotated every single time looks different, and it's hard to see what's the relation between the different instances. Another problem you will have is that it's not always obvious to estimate what is the full extent of the instance, even if you use some kind of boundary estimation of some kind. Another difficulty you will have is that the semantics of what is being annotated is not so obvious. For instance, here you have a point that might be indicating text, might be indicating label, that might be indicating the glass bottle, might be indicating glass bottle together with this weird cork. And the final problem that plague this domain is the issue of co-occurrence. So if you're trying to annotate a sail, almost every single instance of sail you'll find is together with a boat. So it will be very hard for the model to understand if you're trying to annotate only the sail or the sail with the boat. And at the end of the day, to the best of my thinking, there's only two sources of information that every one of the weakly supervised techniques uses. There will be priors and there will be hints. Priors is whatever you believe to be true, independent of any particular image sample or annotation. Is what you know about the problem before even starting looking at the data you have collected. While the hints are those indirect supervisions that you have received for each one of the image on which you have some annotations. So let's try to visualize this in an abstract way. So if we think of the space of all possible models that you're trying to learn, this will be this green region here. Each point in this region corresponds to one model that has been trained. If you have a prior, this tells which region it's allowed for your model and which area is most likely to be true and which area is unlikely to be the true correct model based on what you know a priori. And then every time you receive a hint, this will constrain the space of possible models that could exist because it needs to explain this one hint that needs to be provided. It needs to be consistent with it. So this will reduce the space of possible models to the one under this purple region here. And when you add more hints, then your model gets constrained in the intersection of those regions. With more and more hints, the region or viable models get smaller and smaller. And at the end, you have a much smaller region on which we will select one model that is most in accordance to your prior within that region. So that's the abstract idea. Let's look at some concrete example of priors and hints that have been used in the literature. So the most common prior available is a prior on size. And many of these priors come either implicitly or explicitly in the system. Sometimes the papers won't mention it, but it will be encoded in the hyperparameter or in some subtle aspect of how the model architecture operates. So in this example where you have a bunch of different cats, you might know that in your domain, because of how the pictures are taken and the distance to the subject, actually most cats have a very regular size that is known in advance. And this can be exploited. For instance, sometimes some models have a very specific receptive field, and that receptive field matches more or less the size of the objects that appear. That's an example of how you can have the size prior being implicitly cooked inside the system. Another example is you might have priors on the shapes. Some methods assume that the shapes are convex. Some methods assume that the shapes have a star form. Many methods don't work if there's a hole inside your method. So these priors on the shapes. There are also priors on the locations. This might come by a center bias, where the picture is taking a picture of the subject, so subjects tend to appear in the center. This is commonly used, for instance, on techniques that try to do Webly-supervised object detection, where you initialize with a box that is roughly at the center of your image, because that's a pretty good guess, and you can use that implicitly in your system. Or you also have a location prior that comes from the ground and gravity. So given an image, you can estimate the ground relatively well, and then you know that the objects of interest are most likely to be on the ground. So this limits the region where they appear, and also can be tied in with a size prior regarding how close they are. Another type of prior that is used is the number of instances. Many papers actually assume that there's a few instances or even only one instances, and then they treat more instances as noise. So this is a common prior that is being baked into the models. And again, you want to be careful if this is done explicitly or implicitly. Can you change the number, for instance? One of the most prevalent priors that is exploited by the techniques that do Webly-supervised semantic segmentation is the idea of contrast. The idea that whatever you're trying to segment is not camouflaged on the background, but is some kind of saliency with respect to the background. And usually that comes encoded in two forms, usually of transfer learning, where you're going to, on one side, transfer information you have learned about class agnostic boundaries. Since already quite a few years, we have pretty good techniques for class agnostic boundary estimation, which allow to separate different regions of the image that are most likely to belong to different objects. Similarly, another way to encode this contrast information is through saliency, which not only exploits kind of a generic notion of background that has been learned, background appearance, but also exploits the composition on the image, where again, it assumes that the image is intentional and does show a subject that can be estimated. In this example, you can see that the person with a motorbike gets segmented right away without needing for additional information, or here you can have part of the person being segmented out. So this is a powerful prior, the contrast prior. Another type of prior that is assumed is that if you're annotating videos, then the subject of interest is going to be moving, and that allows you to separate it from the background itself. Finally, then you have class distribution as a common assumption, which is you're assuming that you know something about how often different classes appear. So in this example, you know that cats like to be on cars, so there can be only so many cats given the number of cars. And this again is something that sometimes is explicitly put into the system and provides the and is required for the system to work effectively. So you want to be aware of the priors that your system uses. Finally, one of the key priors that almost every Webly-supervised semantic segmentation technique uses is the idea that, well, there is a similarity within the image of the class of interest. So in this example, cats look more similar between cats than cats will look to the background. And this allows to basically do some implicit matching inside the method. And this, for instance, can break down in classes that have a very diverse appearances. So an example of chairs chairs can be very different, and if you have a small data set, you might not find another chair that is very similar to the one you have. And this can be improved if you have very large data sets, but this is one of the common assumptions. As an example here, I put a recent work that very explicitly model these pairwise relations, but is implicit in basically every single weakly supervised segmentation paper. And the last prior that I think is worth mentioning is that there's also some methods that exploit external datasets. So they will do that either through transfer learning, or they will do that through retrieval of existing image. So they assume that the image that we're currently annotating also are somewhat similar to other images in the world that are available. And that's part, or no, it's one of the implicit prior the system has. And if for some reason that's not true, those methods will break down. All right, so that's a list of priors that have been used in literature. There's some more, but I think these are the main ones that are worth being aware of. Let's talk about the hints. So these are different clues and cues that the system, that the annotator will provide to further inform which model should be trained. So the most common one, which there's a bunch of literature here, just cited some of the well-known papers, will use image level labels. So image level labels indicating the list of classes of interest that are inside the image, and that's what you have to train your model. And we're going to discuss later an example of work that uses this. More advanced version of image level labels is image captions, where you have natural language used to describe the scene. And again, this has been used in previous work to do weakly supervised semantic segmentation. You can do the similar things for videos, right? Where you have video with image level labels. And here it also matters that there's a temporality, right? So either you are cutting your video in snippets and providing labels for those, or indicating each one of the labels how long they last in the video where the object is present, or the class is present. You have a similar prior, similar hints that you can provide by explicitly giving datasets where they have been curated, such as is true, the prior that I provided before, like before you had a prior that this was true, but you can also provide this directly as a hint that you're saying, I have collected this dataset explicitly to be somewhat similar to the target dataset, and you use that as a hint. And there's also the idea of transferring across classes. So you provide not the images, but in this case, you provide information about the relation within the classes. In this diagram, this will be, you know which classes are a subset of others, and this allows you to propagate information from one set to the next. And that's an explicit hint. Finally, going into more direct annotations, you have quite a few work who have considered the idea of clicking on the object. So instead of segmenting the full object, you just click one or a few clicks on the object as signal for weakly supervised segmentation. There's also an interesting observation done by this paper where they show that if you have 2 clicks or 3 clicks on the object instances, then there is a bias in how humans annotate, where if the points are very close by, then you can estimate, you can guess that the object is small, while if the object are a bit separate, if the points are a bit separate, you can estimate the object is big. So this is a signal actually only from clicking at the center of the object, you get a signal about how big the object is on the image, and this was exploited in this paper as an additional hint for training the model. Then the classic, the second most classic, probably weakly supervised segmentation hint is providing bounding boxes. And again, there's a bunch of paper on this. I just picked a few here. You provide a bounding box with the class label, and then from there you want to get pixel level annotations instead of just bounding box annotations. And we're going to also discuss example of this kind of techniques. A variant of drawing the bounding box is what's called extreme points, where you're still providing the information to have a box, but you're explicitly clicking on the object. These are the extreme points on the object, so that provides an additional cue for the segmentation tasks. And this has been shown to be better than just drawing the box, while actually being faster to draw than drawing a sliding box. So this is how you should be drawing your boxes if you care about segmentation tasks downstream. Another classic type of annotation is to use scribbles, either a few points or very dense. This is basically a generalization of clicking inside the object, and those scribbles also can provide information about the class or the instances, depending on which type of annotation you provide. And this is still unclear if it's much better than providing just a few points. So no, scribbles takes more time than just a few points, and where is the good trade-off between time and quality is still an open question in my view. Another interesting type of hint that's been used explicitly in a paper is the idea of eye gaze. So you can have a person looking at an image and then have a camera look at the eyes of the person, and then the person will be describing the scene and at the same time looking at the scene, and they will naturally be looking at what they're describing. And this provides a soft cue of where the different mentions are, and this has been used for weakly supervised learning in the past. And now there's a paper at this conference that actually uses a variant of this idea, where instead of using eye gaze, you can use your mouse. So it's a somewhat more generic approach. So they will be recording the voice of the person as they speak, and as they speak, they're asked to point with the mouse basically of what they're speaking about. So you end up having a temporal sound signal, you end up having a temporal mouse signal, and then they ask, or this is either manually done or automatically done, the text they said gets transcribed, and this is time aligned with the mouse trace. So you obtain a denser description than standard caption, and those denser description are aligned with the trace on the image. So it's partially loose, but it does provide a strong hint of where different things might be. And this is a recent type of annotation, which is somewhat of an extension of scribbles and eye gaze and captions put together. And it's probably going to be an interesting type of data to use as a hint in future works. So those are examples of common hints that have been used in literature to train weakly supervised models for semantic segmentation. So it turns out that there's a recipe then to make a paper if you on this area. You just select a specific set of priors, you select your favorite set of hints, and then you choose an application domain on which you want to showcase that this works, and tada, you have a weakly supervised paper. This also means that when you're reading a paper or looking at a poster, you want to check which are these ingredients that are in the method. So if you're going to visit virtually, I guess this year, a poster, you want to ask which priors are being used. How are these priors being encoded? Which one are explicit? Which one are implicit in the architecture? And also you want to know which information sources are used. Which are those hints that are being available? Some of them are baked in the pre-trained models. Some of them are provided explicitly in the description of the system. And many papers actually exploit this new type of hints, and you want to understand why was that source not exploited before? What is the new unblocker that allows you to do that? So that's basically a way to think of weakly supervised learning papers, and invite you to kind of take this perspective when you look at new papers or when you think about creating a new paper in this area. So let's start talking about specific methods for weakly supervised learning. In this example, starting from image level labels. So you want to train to localize where you didn't provide any localization information. So you have, for instance, here you know that there's a person and a bicycle on this image. These are available on your training set. And then you want to be able to train a model that at test time will provide pixel level labels for those classes of interest. So there are two main approaches in my mind how to go about it, what I will call Greybox approaches and white box approaches. So a very common Greybox approach thinks of first you train an image classifier, and then you compute the derivatives of the image respect to the sum of the classes, and you ask basically how much this pixel change will affect the score of that class. And this provides this kind of interesting masks that are somewhat correlated to the object of interest. And this idea is pervasive. There's quite a few papers who explore this idea in multiple ways. However, you have to be quite careful with it, because if you think about it, if your model is a perfect classifier, then it should be invariant to small perturbations on the appearance of your object, which means that if you do a small change on the appearance, in this case of the bird, then it should make a zero change in the score. So the better your model is, the worse the result of this method will be. So in that sense, I'm willing to claim that this is conceptually flawed. It worked in practice with the models we had at the time, but is doomed to fail more and more as we push forward the area. So it won't work if you have a linear function, it won't work if you have a good classifier, it's not something you want. And as I said, there's a lot of literature of different variants around this. For instance, one of the variants that is easy to explain that I liked is that they will do the same process, but first they will add a bit of noise on the image, and then we'll try to estimate this derivative. And then they will repeat this 50 times and average the results. So visually, this provides nicer results, but many of those papers actually have relatively weak experimental sections, and you will see that they don't have strong evidence that this is actually better. And they can't, because the method, the general approach is somewhat flawed. So at the end of the day, these are train and pray methods, I call them, right? So you train an image classifier, you do something, and you pray for the best. And this is somewhat doomed to fail, because a classifier was not built nor trained to segment object. You're trying to get oranges, apples from an orange tree. So something different needs to be done. And this would be the white box approaches. In the white box approaches, you don't just take an existing classifier, you allow yourself to modify the architecture so that it goes closer to what you want to have. So you change the network architecture, and one of the most popular ways to do this is what's called the CAM technique or the gap technique. And it just takes an existing classifier, and instead of having a fully connected layer at the very end that goes from the last convolution layer into the class cores, you're going to replace that by having a spatial average pooling or global average pooling gap. And then this will be the final score. And because of how the layers operate, you can actually convert these last operations and move the average spatial pooling one layer below. So you will have convolution layers, global average pooling, and then 1x1 convolutions, which will provide the per class cores at the very end. So this is some kind of latent spatial distribution of the things that interest for the class that you want to classify. Okay, this is another visualization of same idea: convolutional layers, global average pooling, and then these layers are so-called class activation mappings or class activation maps, and the last 1x1 convolutions are doing a weighted sum of these activation maps, so that you obtain the final activation maps for the class of interest, which is then it's basically average pulled into one number. So when you train a model like that, you're explicitly forcing the model to decompose different areas of the image in parts that will be combined, such that you obtain the class of interest. You could obtain the score of the class of interest. And this is quite powerful. For instance, you can trivially use the different ways for different classes to ask the question, given an image, which is the support for the different classes. And here you can see that, for instance, Palace will take most of the building, while Dome will focus on the upper parts, and so on and so on. So you can really see that this is the composition aspect. And also, empirically, has been shown to work better than this previous technique that I mentioned that are used to look at the derivative. And this is somewhat expected, because at least this method has a chance of providing what you're trying to do, because you have built an architecture that is done to do these per class maps. So the way these per class maps are used, just to be explicit, is that once you have the per pixel map after the weighted sum, then you're going to threshold this map into a binary mask. So you take the high value pixels that have high scores for a given class, and you will treat this as foreground pixels for that class. And then the low score regions are going to be considered background, right? If no class activates strongly, then that's likely to be a pure background area. And then these foreground and background areas become what's called seeds, which are basically hard decisions that are used to then train a semantic segmentation model. So you first train your classification model, you obtain the seeds for which you're going to train your semantic segmentation model, which is usually your final result that you can evaluate in a traditional way. So as you have seen from the examples, this works better than nothing, but there are some obvious flaws. The first one is that the resulting masks are not sharp at all, they're very blobby. And the second one is that they only focus on the discriminative areas that allows to do good classification, but it's not guaranteed that they will have a bias towards covering the full extent of the object. And that can be improved with some techniques. The first one is that one of the reasons the maps are so blobby is that the classifier that we use initially and is commonly used actually have pretty low resolution at the top layers. So if you just increase the resolution of your classifier, you have a hope of having better masks. In practice, if you just do that, it doesn't work quite well, but at least there's some area that you need to further modify the architecture to be able to do high resolution outputs. So one landmark paper in this field that tried to fix this issue of not being sharp on the boundary, it's so-called the SEC technique, which basically combines three different ideas. The first one is that you will do your global edge average pooling to have a classification loss, as explained before, with some small modifications, but the idea is the same. Then you will use these activation maps and threshold them to obtain the seeds, and this will become the seeding loss, just as I explained before. And they add a third ingredient, which is a CRF. So basically, they will take the current results of the model and then run it through a CRF that uses basically a boundary prior, such as after propagating the labels, you get labels that are matching better to the image boundary. And then the nice idea is that then use these refined masks as supervision for the semantic segmentation model. So as the training goes, the model is incentivized to generate segmentations that are more aligned with the boundaries, such as when you run the CRF, you will get the same results. So at the end of the training, ideally, taking the mask and running through the CRF will give exactly the same output as the output of the model. So that's a way where you're forcing to respect the areas that the model considers discriminative for classification, and then you're expanding them through this global average pooling, and then you're contracting them through the CRF. That's kind of the mindset how they present it. And this is quite effective, although it has quite a few hyperparameters that needs to be well tuned. Another way to have sharper masks is to use another type of priors. For instance, you can use a silencing information that has been trained to better respect the object boundaries, albeit is unaware of the classes of interest. So you can combine these two informations to obtain better segmentations, as explored in this paper. Or you can also use equivariance ideas. So you expect your model to be equivalent to translations or small deformations, such as the class activation maps should be the same if your image is a bit smaller or a bit bigger, if it's a bit rotated or not. So in this paper, they propose to add an equivalent loss into the system, such as you take the image, you apply the cam technique, then you transform the image, you apply the cam technique, and then you can unwrap this transformation and then compare the two. And this will be an additional loss to supervise the training that forces then the model to better cover the object. They had some additional ideas how to better respect the boundaries, but this equivalence idea, I think it's a very generic and useful idea that works well in practice. So those are the ways that you can make the mask a bit more sharp and to cover a bit more the object, but there's still not an explicit signal to focus on the discriminative areas. And for this, one of the ideas that I liked is what I call the peekaboo technique that was proposed, where you're trying to hide some areas of the image. So this is identical to the spatial dropout idea, but no presented in the context of Webly-supervised learning, where you just say, well, I'm going to train my classifier, but instead of just providing the image, I'm going to also drop out part of the image. And this forces the classifier to be aware of the different areas of the object that are discriminative. Not just the main one, but also every other part, because once in a while, for instance, the heads usually are discriminative. Once in a while, the head will be occluded. So this provides better results, where you can see that with this dropout technique, then the extent of the object is better covered by the activation maps. An evolution of this idea is instead of just doing random dropout, you can also do adversarial occlusion, where you're going to remove, in this case by graying out, the part of the image which is already considered by the classifier, and then you train a new classifier on this with these occluded regions. And then you keep repeating this process by increasing the occluded regions until the classifier quality drops significantly. So this then allows to mine different regions that can be used to then do the Webly-supervised segmentation, and in a sense forces the model to be covering more and more of the full extent of the object. And again, empirical results show that this basically moved from different regions, from the head to the body to other parts of the body, and provides better signal than if you just use the naive gap technique as described. And of course, this does provide better results in practice, thus it's worth mentioning. So some takeaways from this section are that if you're going to just train a classifier and hope to get segmentation after that, you should consider that this might not work at all, and something else needs to be done just than train and pray. And there's some techniques that have been used to force to have special continuity priors. This will help a little bit, but only so much. They don't provide a dramatic change to the results. And what seems to help even more is to actually change the training procedure to force the model to cover better, and also to force the model to respect better the object boundaries. So it remains an open question how far these techniques can go. It seems to be that if you have enough images and well-crafted priors, this task could be done very well. And it's still an active area where every conference you see more and more papers try to push the task of pixel level labeling starting from image level labels. So I invite you to read the recent papers and explore some of these ideas now that you have a framework to think about it. All right, so let's move on to a related idea that I think is worth mentioning. I will go quickly over this part, which is the idea that, as I mentioned before, one of the priors you can exploit is the fact that you have similarity between the image of interest and every single other image available out there. For instance, when you do Webly-supervised training. So the key point when you do Webly-supervised is that the web contains different type of images with a bias towards somewhat simpler, more prototypical image of the object, and this can be exploited. So in this CVPR 18 paper, they propose to think of the target domain you're interested on and the web domain that is basically every single image that has similar keywords that you're interested on. And they propose to first train an image classifier of the target domain, and then they use this classifier over the web images. This allows to select only web images that have objects that are similar to the target domain, and then they apply some of these image level label to pixel level label weakly supervised technique to obtain a model that can segment the class of interest. And the key idea here is that if you do that over web images, because those web images are somewhat more simplistic, then it's most likely that this model will be quite good, because it has the chance to actually use the priors, exploit the priors to get good segmentation on those simpler images. So then you train a semantic segmentation model from the web domain, and you can apply it over your target domain, and you can also apply the weakly supervised techniques on your target domain, so you end up with two sets of segmentations which have different strength. So the authors think that, well, the Webly supervised segmentations will be very good in localization, but they tend to be at least observed that they have some mistakes on the classes that are present, while the in-domain weakly supervised model is very good at having all the classes, but the localization is a bit inaccurate. So they have some heuristics of how to combine these two. They obtain enhanced masks on which they can train their final model and get better results, as expected. It's also interesting that with respect to the baseline that they're considering, the results they get from web supervised are actually quite close to the fully supervised scenario. So in general, it makes sense that if you have more images available, you get better results. And this paper shows, I think, an interesting approach of how to do that. So that's another way you can improve your results, is by leveraging larger data sets. And this trick of using the image classifiers to select images that are somewhat closer to the domain of interest, I think is a good general idea. And the last paper I want to mention, going from image level label to pixel level label, actually goes not only for semantic segmentation, but goes for instance segmentation. So this is clearly a harder task. And most of the papers who tried to do that before, they were leveraging strong priors or strong transfer learning techniques, where they will train some form of mask information, some form of boundary information, even sometimes some form of instance information, and then show they can transfer it in the target domain. This paper, however, is the first one and the only one I'm aware of that actually only uses priors plus the image level labels to do instance segmentation. So in that sense, it's a pure technique. There's no pre-trained silicene, there's no pre-trained boundary detector of any form. And the insight I have is this one key idea is one way to phrase it would be that, after doing thresholding, if you do carefully your class activation maps, then that is actually quite good. And you can do more than I would have expected by exploiting it. So they will do some refined version of CAM, where they get these seeds images. Here the white areas are unknown, black is background, and the other ones are the class of interest. And then they look at a small neighborhood of a given, of any arbitrary pixel, and they would see that, well, the center pixel is of a given class, and then the neighbor pixels might be of the same class, of a different class, or no, they're ignored regions that are unknown. And with that information, they're going to train two models. One would be a boundary detector, where they basically say, well, between this point and this point, there should be no boundary, and between this point and somewhere in between this area, there must be some boundary. So they have a multiple instance learning formulation, where they say that along certain rays, no, a boundary is known to exist at a given distance. So that way they can train a surprisingly good boundary detector from CAM information. And then even more surprising, they will use the connected components and assume that if, in general, this is true, if you have two neighbor pixel, let's say this center pixel and this other pixel from the same class, then they're most likely belonging to the same instance. That means that the centroid of this connected component, which would be somewhere around here, is a good approximation of which is the centroid of these two pixels. So they will learn to regress from a pixel to centroid of the object, which is visualized in these rainbow colors. So the rainbow indicates the direction, the intensity indicates the distance that you have should jump. So here, if you're in this point, you should jump this far to get to the center. If you're in this point, you should go this far and this direction to get to the center, and it gets whiter towards the center because then it's smaller and smaller jumps. And they only train this on the foreground classes. So this works surprisingly well. And then once you have your class activation map, a boundary estimator, and a centroid predictor, then you're able to estimate masks by basically solving an optimization problem that combines these three signals together. And these are the kind of instance segmentation masks they get that they can then fit to train an instance segmentation model to further refine the whole thing. So it's kind of shocking that you can do that at all. And to the best of my understanding, they're the only one paper that actually shows that this is possible at all. They get reasonable results, right? There's no real comparison point, but looking at some older techniques that use different models, they show that they are slightly better than other techniques that use boxes before. And when they compare for the semantic segmentation task, they show they're also state of the art when you use only image level label, and you're comparable to other techniques that use more information. So it's definitely an interesting paper that I invite you to read. There hasn't been much follow-up on it yet, but they show how far you can go when you exploit well this information that comes from the class activation maps, as I explained before. Here are some qualitative examples, the ground truths, the obtained results. And remember, this was only obtained from image level labels, and again, exploiting some of the priors, in this case, how simple and large the instances tend to be in the Pascal dataset. All right. So let's move on to the more traditional setup for instance segmentation, which is you would like to start from box level labels to go to pixel level labels. And then it's naturally easier to obtain instance segmentation results. Right, so from boxes to instance segmentation. So before we go into the more advanced techniques, let me start with a baseline idea, which is I'm one of the co-authors of this work too. So the idea here is that what we want is to have these segmentations, which then later will become instance segmentations. And we start from, if you have a box, if you look at it from far away, it kind of looks like a segmentation, just like a very rough, very bad segmentation. And we wonder ourselves, what happens if we just train with that? Just train on Troid in training a model. And what's interesting is that with modern models, you actually, when you train your model over this supervision, the model fails to learn the task. It actually does not learn to predict a box. It learns something a bit worse respect to the box. But actually what is happening is that it takes what is the consistent relation between appearance and the output gets selected, and the inconsistent relation between appearance and the output gets averaged out. So after one training round, you get a segmentation mask, which is closer to the true object than what you started from the boxes. And then we wonder, well, what if we repeat this process and feed this segmentation mask as training data for the model? And we keep looping and looping. And after 10 rounds, you can see that the segmentation masks are significantly better than when you started from, which are just the boxes. We're doing nothing more than just training a model in relatively standard way. So when we evaluate this at the time, we see that just using this iterative training of rectangles, we get very close to what was the best previous results on this field on the Pascal dataset. And then if we do something a bit smarter, like for instance, we exploit a prior, which is, we know that the rectangle is probably a bad approximation of the full extent of the object, but since more objects are somewhat potato shaped, then the center of the rectangle is more likely to be on the object than any other region of the image. So if we set the center region to be a seed, and then the outer region of the rectangle to be ignored regions, and then everything outside of the rectangle to be backgrounds, then we do this iterative training, and right away we got better results than state of the art at the time with such a simple idea. So do consider baselines, do consider simple ideas when you start in a new area. And this whole thing exploits the fact that the covenants are surprisingly robust to noise. A similar effect was used in the previous work that did instance segmentation for image labels. And if you do something a bit smarter than just do this center region, if you do some kind of graph++, then we show that this was right away better than was done before. And these are example results where you have the image, this is a ground truth, and if you use either this center region or the graph++, you get visually good results. And since we did all of this process per box, then we can right away do exactly the same thing. Instead of training a semantic segmentation model, we can train an instance segmentation model. And again, at the time, few works had done instance segmentation, and we show that this works reasonably well with the models available at the time. So simple baselines already work quite well. So let's see what could be a more advanced technique. So the idea of this ECCV 18 work that I want to present now, it's an example of a more sophisticated approach, and it's a technique that I think is somewhat elegant. And the idea is that, well, if you can do instance segmentation, that means that you can segment out an object and paste it in a different area of the scene. So if you observe this image for a few seconds, you might notice there are a few things that are weird on this image. So for example, you might have noticed that this car appears twice, or you might have noticed that this car actually is going in the wrong direction, or that this person appears twice too. So the reason this happens is because it's a synthetic image. It's actually composed out of this training process that we're going to describe in a second. So the key idea is that if you're able to predict a mask, then you're able to cut out the object based on the mask and then paste it in a different background. And that result should look a somewhat realistic image if your mask was good. If your mask was bad, then you will have only kind of cut out a partial object, or maybe even including some backgrounds. And then when you paste it, it will look quite fake, which means you can train a discriminator in a GAN-like mindset, where a discriminator trained to recognize real images out of these composed synthetic images, and that can be your supervision signal to the full system. So if we look at a different view of the same idea, here you have an image, then you have a model that is able to do instance segmentations. Then you can crop out the object of interest and then paste it in different backgrounds, and then have this discriminator per recomposed instance to tell if this is real or fake. And these are examples of how this looks like. So the top row are real crops of an instance, and the bottom row are recomposed with a different background. Again, we can do this because we're assuming we start from the box annotations. And you can see that from a quick look, the recomposed image look quite good, which means that the model actually has learned the task of masking out the object. And this to me is quite surprising. You can do this end-to-end training of exactly what you want. One of the limitations of the approach is that if you include the shadow of the object, this also recomposes well, so you cannot tell apart the shadow from the instances. But on that, it works surprisingly well, and again, obtains good results at the time of publication. And this shows that you can also use more sophisticated ideas to tackle this task. And these are examples on the Coco dataset. So they are not quite perfect and not quite accurate, but again, this can be improved by improving the model architecture. The itself is more powerful, and maybe adding some of the priors that I mentioned before through some of the techniques I also mentioned before. All right, so that covers what I wanted to discuss today. So some takeaways that I would like you to remember is that there are many priors and hints that have been explored in the existing literature, and you want to be familiar with them and think about them when you're tackling your own tasks. And you want to exploit basically all available priors, all the priors that are true, that are relevant for your domain. You want to use them, and you want to think about new sources of information that might exist that you didn't think before. Like this example of speaking and moving the mouse. Takes about as much time as other notation techniques, but they're richer right away. And you might have some other form of information that you're not thinking of. And all of them can be used as hints for your weekly supervised training technique. I want to reiterate that the transfer learning is an extremely powerful technique in practice, and many papers kind of shy away from it because they want to have this pure, clean setup where they can compare from one paper to the next. But in practice, you are allowed to use all the data you already have in your company or in your project, and this will allow to significantly improve results compared to like pure techniques. And similarly, web supervision is also likely to be an area that, as we grow into bigger and bigger system, is going to exploit more and more of this prevalent, already supervised data that is out there on the web, where people have taken a picture of an object, put a white background, and mention with text what this object is about. And I also want to mention that when you look at the numbers, the current techniques in weekly supervised segmentation are actually quite effective. And many of them do ride the wave of better network architecture. So you can use the same technique, update the model, and you will get better results, at least in absolute numbers, and potentially also in the relative number respect to the fully supervised case. So for now, this field seems to be quite promising, and I hope you have learned something interesting today, and that you will think about this framework when you read new papers, and also think of this framework to create your new papers in this area. So that's all I had today. I invite you to watch the other videos of our ECCV tutorial. Some of them talk about weekly supervised techniques for object detection. Some of them talk about human-in-the-loop annotation processes to complement just the weekly supervised labels you might have at the beginning. And some of them talk about evaluation issues you have when you do weekly supervised techniques. I hope you enjoyed this session, and have a good day. Bye.